we are going to go into the differential and integral calculus with tensors. What we have done so far is simply tensor algebra. Tensor algebra tells us what a tensor is, the properties of tensors, how they add, how they multiply, and the characteristics of tensors such as the invariants, functions that you can form on them, how you can decompose them. All those things are all in the realm of algebra of tensors. So you are like somebody who has been learning algebra and is now being introduced to calculus. The calculus, the differential and integral calculus that we are going to do now is different from the differential and integral calculus you have been doing. The differential and integral calculus you have done so far are the differential and integral calculus with scalars. All the time you are interested in x-axis and y-axis. X-axis is scalar and y-axis is scalar. You have two scalar axes and you are relating functions on one axis to the other. The function itself is a scalar and its argument is a scalar. The domain is a scalar domain and the range is a scalar range. We are now going into a situation where either the domain can be vector or tensor, and the range can also be vector or tensor. It is possible to have a tensor function of a scalar function of a tensor. Both will be possible. So when we are differentiating, we do not presuppose that either the independent variable is a scalar or the dependent variable is a vector. We don't know. So we want to expand our knowledge so that we can work with those things. And that takes us to the realm of tensor analysis or the differential integral calculus with tensors. This is different from whatever else you have done thus far. So we are getting new information, you are getting new mathematics, you are advancing your mathematics to another level. We will not take this from a mathematician's point of view. We are going to take it from the point of view of an engineer. I want to quote Martin Gottin, who is the best author in this area that I know. He said, we do not force over smoothness assumptions. Functions and boundaries of regions are presumed to have continuity and differentiability properties sufficient to make meaningful underlying analysis. So I will not be talking like a mathematician, if the thing is continuous, if it is smooth, if it is this, if it is that. We assume that all those basic conditions are met with the functions we are dealing with, so that we can go straight to the point. So this is the scope of this lecture. The issues that we are covering are not hard to understand. They are fundamental to all tensor analysis. They are not hard, but you must pay attention. Be careful to note any area of difficulty, and if you are specific, you can receive assistance. We will introduce the Gateau differential as the solution to our inability to divide by tensors when we want to define a derivative. We will remind you that when you define a derivative, there is a division involved, but you cannot divide by a tensor. Tensor division is not allowed. Vector division is not allowed. In fact, division is not defined either in the vector space or in the tensor space. Therefore, how do you differentiate with respect to a large object, such as a vector or a tensor, when neither of these spaces allows division? So what do you now do if you now want to define a derivative? So we are going to define it with a very careful and very ingenious way to do things. And that ingenious way is called the Gateau differential. We will introduce it, we will define it, and you will know everything you need to know about it if you pay attention and you are ready to be alert. So we will talk of the limit of a quotient. That is what the derivative is. Sorry, sir, I'm in a class. I'm teaching. I will call you after my lecture. Okay, sorry about that. So we will look then at the important consequences in 3 examples. Then we will talk about how tensor arguments creates a problem. You cannot divide by a vector or tensor. How can you differentiate with respect to a tensor? the solution is the Gateau generalization of our usual directional derivative. We did directional derivative last term, but we are now going to generalize the idea with what is called the Gateau derivative. And you can now differentiate with respect to an object of any dimension. When we did our directional derivative, we were looking only at vectors. We couldn't go further. The reason being that we had not done tensor algebra. Now we have done tensor algebra, we can carry that to a much higher level. So differentiation and large objects. We are already familiar with the techniques of differentiation of scalar valued functions with respect to scalar argument. So when you have a scalar valued function with respect to a scalar argument, there is no problem. But if you have a scalar valued function with respect to a vector or tensor argument, there is trouble. All your formulas will not work because your formulas involve division. You can't divide by a vector, you can't divide by a tensor. These objects, but the objects that are defined in the scalar domain, where if let us say you have x and h that are real numbers, then the derivative f prime of the function f is defined as f prime of x, which is the limit as h tends to 0 of f of x plus h. You evaluate the point as a near point, just perturb it with a variable h. Just move a little bit away from x by h, then subtract it with the value of the function at x, and then divide the difference with h. This poses no problems as division by scalars is well defined. But what if x is a vector and h is a vector? Can you therefore write the derivative of x is equal to f of x plus h? X plus h is still possible, even if x and h are vectors. F of minus f of x, which is still possible. But when you now divide it by the vector, then you are in trouble. Mathematics, you are no longer doing mathematics, you are doing juju or some other thing. It's no longer math. So the question is, can you still define derivative even when the argument is a vector? Or when the argument is a tensor? Can you? The answer is you can. And that definition is related to this. So we are going to do it related to this, and you can connect the two, and you can see that it is a properly defined way of differentiating. So let's go on. Large objects, scalar arguments. Things become more complex when we handle tensors. The second order tensor contains 9 scalars. A vector, which is a first order tensor, contains 3 scalar members. This complication does not arise from the size of the objects themselves. It is not the size of the object that causes complication. Derivation of tensor objects with respect to scalar domains are possible. Despite the fact, if you want to differentiate a vector, you've been doing that. You can differentiate a vector with respect to time. It just gives you 3 scalar differentials with respect to time. But suppose you want to differentiate time with respect to the vector. That is where the problem comes. Derivation of tensor objects with respect to scalar domains with some adjustment basically conforms to the same rules as the above derivation of scalars. Division of a tensor by a scalar is accomplished by multiplying the tensor by the inverse of the scalar. So you can always differentiate, you can always divide a tensor by a scalar. That is the same thing as a scalar multiple that is the inverse. That's all. This operation is defined. So you can always multiply any tensor or vector with a scalar. Whether if you can multiply with a scalar t, you can multiply with the scalar 1 over t. If you are multiplying with 1 over t, that's the same thing as dividing it by t. So that is all you need to do. So we can define. So here now, look at this. Let us say t is a tensor, and this is a function of a scalar argument. Or no problem with defining the t of the tensor. It's simply the limit as h tends to 0. Remember that h is a scalar of t of t plus h minus t of t over h. So this quantity, this quotient is still defined because what you are dividing by is a scalar. The argument, the independent variable is a scalar. So this is no problem. So instead of dividing by h, you can say you are multiplying the difference by 1 over h. Still the same thing. The product of the scalar 1 over h and the difference of tensors are defined, and they are tensors. Hence, the derivative of a vector or a tensor with respect to a scalar, is either a vector or a tensor. If it is a tensor vector you start with, you get a vector back. If it is a tensor you start with, you get a tensor back. So you can differentiate a tensor with respect to a scalar. You can differentiate a vector with respect to a scalar, and you have been doing that all along. You have been differentiating vectors. You can differentiate the velocity vector and get acceleration. You are differentiating with respect to time. That is possible. No problem. So large objects with scalar arguments. So if you have alpha times t, so this alpha is a scalar, t is a tensor. If you want to differentiate the product, the answer is alpha, you differentiate one, and then you differentiate the other t. Each of these two terms is a tensor, because here alpha is a tensor, alpha is a scalar, but the big T, the T is a tensor because it doesn't change the tensor nature when you differentiate with respect to a scalar. And in this second one, the alpha, if alpha is a scalar, the alpha, the T remains a scalar, and it's not a scalar multiplying a tensor, which thing gives you a tensor. You can work this page out. I don't want to spend time on that because everything there is a bit simple and straightforward. We didn't omit any work in there, so that should be clear to you. Large object scalar argument. Remember where you are. Proceeding in a similar fashion for alpha, which is real, for u and v, which are vectors, and s and t, which are tensors, all being functions of a scalar variable. So you can have a scalar that's a function of a scalar variable, a vector that's a function of this vector of the scalar variable, and a tensor that is a function of the scalar variable. All being functions of scalar variable t. The results in the following table holds as expected. The simple rule, when obeyed, allows us to gain proficiency and transfer knowledge to tensors. But don't be fooled by the symbols. They are overloaded because when you say plus, when you say u plus v, let us say I have a vector u and I have a vector v, and I say u plus v. The plus there looks like the plus when I say 1 plus 2. But you know that adding vectors is not the same thing as adding scalar numbers. Because that plus in the vector addition, you are adding you are having three different subs. If it's a tensor addition, you are having 9 different subs. So that plus sign is overloaded. It has more meanings than meets the eye. So don't be fooled by the symbols. They are overloaded. You are no longer in the real space. You are now in a Euclidean vector space, and the rules are different. So remember where you are. If you don't remember where you are, you will make mistakes and you get punished. So this is the full set of relationships when you are differentiating vector and tensor functions that are functions of a scalar variable, and you are differentiating them with respect to the scalar variable. These are things you've been doing before. And so if you are differentiating a scalar multiplied by a vector, this is what you get. You are differentiating a dot product with respect to time, this is what you get, or with respect to scalar t. You are differentiating a vector product, this is what you get. You are differentiating a tensor product, this is what you get. Here, the thing becomes complicated in these two cases. Remember that these things are not commutative. You are not allowed to write this one as v cross b u dt. The relative placement of u and b must be maintained at all times. In this case and in this case, because they are not commutative. When it comes to the scalar product, it is commutative, but when it comes to the vector and tensor products, these things are not commutative. Again, when you get here, when it's just a simple sum, there's no problem because there's linearity here. So the differential operator is linear when it is operating on the sum of two tensors. Now, but when it's operating with these two tensors, again, here, the location and the direction of t and s, that t always comes before s, must be maintained. So remember where you are. Remember where you are. Don't be careless, because t ds dt is not the same thing as ds dt t. They are not the same. So just like, remember in matrices, a matrix A times a matrix B is not the same thing as the matrix B times the matrix A, because commutative laws do not work in the Euclidean vector space. So similarly here, T with the inner product of T and S, differentiating them will give you this. Differentiating alpha, which is a scalar times T. I think that's the one we did. That's the one we did before. Yes, we did this one before. So that is the one we worked out in full. Order is not important when you are talking with multiplication by scalar. Let us take them one by one and let us see. Let me ask, I want to ask the class to be sure the class is awake because this class has been dozing all day. I have how many things here? 1, 2, 3, 4, 5, 6, 7, 8. In this 8, I want you to go to the chat room and tell me whether the rule in 1 to 8 is commutative or not commutative. So let me tell you what you are going to do. I will do the first and the last. The first one is number 1. And I will say it is commutative. So 1, C. The number 8 is also commutative. If it is not commutative, see, 1 is commutative, 8 is commutative. That is, it doesn't matter whether you turn T and S around, whether you turn U and B around. So I want you to go to these 8 things and tell me about 2, 3, 4, 5, 6, and 7. For example, let me say 1, 2, 3, 4. In the case of 4 is not commutative. So I've done 3 out of the 8, and I want you now to do the remaining 2, 3, 4, and so 2, 3, 5, 6, 7. 2, 3, 5, 6, 7. Okay, so I think the class just woke up after the break. So good. It's good that you're awake now. Okay, so let us now move on. If you know that, we're going to start with some examples. And we're going to take the fact that the identity tensor is a constant. And differentiating with respect to any scalar value should give you the identity tensor. So it's a scalar. So it's constant. So from slide 10.6, we recognize the fact that the derivative of tensor with respect to a scalar must give rise to a tensor. The value here is the annihilator tensor or the zero tensor, because if you differentiate it, you are not going to get a scalar 0 because the differentiation of a tensor with respect to a scalar will give you a tensor. This fact that the identity tensor does not change and has a 0 derivative leads to 2 important results. We are going to look at these important results next. First of all, let us say S is a function of T and it's an invertible tensor. That means that it has an inverse. So there is S inverse. Let me correct that because I have to use the same. You have to use the same bold on italicized thing. Since it's I have to use the same bold on italicized. Okay, so S inverse S is equal to the identity tensor. So if we differentiate that product using the rule, what rule now? We are using the rule 6. We use rule 6 to do that differentiation. If we use rule 6 to do that differentiation, so we should first of all differentiate the inverse with respect to T multiplied by S, and then you have S inverse multiplied by the derivative of the tensor itself with respect to T, and the derivation has to be 0 because the derivative of the identity with respect to T is 0. So this must be equal to 0, which means that if you transfer this to the right-hand side, you have minus, and then you post-multiply both of them with S inverse, you have this expression here. So you can express the derivative with respect to T of an inverse tensor in terms of the tensor's derivation itself, which is multiplied on both sides by the S inverse and with a negative here. So this is a result that is coming out of the fact that the derivative of the identity tensor is 0. That is the 0 tensor. So that is one consequence of the. So let us say you want to get the derivative of the inverse. You know the inverse, but it is difficult to differentiate. Differentiate the tensor itself and pre and post multiply by the inverse and take a negative of it. You got what you are looking for without actually performing the derivative. That is if we multiply both sides by S inverse. The following important expression results for the derivative of an inverse tensor with respect to a scalar parameter in terms of the derivative of the original tensor function. So conversely, we can also get the derivative of the function itself in terms of the derivative of its inverse with this. Just if instead of transferring this one to the other side, if you have transferred the first term to the other side and pre-multiply by the tensor S, you get the second result. So these two results are coming from the fact that the derivative of the identity tensor with respect to a scalar parameter is 0 because the identity tensor is a constant tensor. Let us go on, constancy of the identity. So let us take a look at orthogonal tensors. You remember that an orthogonal tensor is a tensor whose inverse is its transpose. So if Q is orthogonal, then QQ transpose gives us the identity. Then we can differentiate this equation. If we differentiate the equation, one consequence of the relationship is that the tensor omega, which is dq dt, multiplied by Q, we have multiplied by the transpose of Q. If we define omega as dq dt multiplied by Q, that tensor must be skew. Why is it skew? This is the proof that it is skew. And it is coming as a consequence of differentiating the identity. Since QQT here, you can see that QQT is equal to identity. That's the definition of the orthogonal tensor Q. So if you differentiate this product, you first of all differentiate the first one, QT, and then differentiate and take the first one and differentiate the second. And since the two of them are equal to the identity, it's simply a differentiation of the identity and gives you the annihilator tensor. Again, that means that this equation is equal to 0, the 0 tensor. You can transfer one to the other side. If you transfer this to the other side, and then you know from your matrix algebra that if you take the transpose of everything, this equation here, if you let the transpose sign cover both Q and this one, you have to reverse them. So then transpose this one. So that is this one is minus dq dt qt, all of it transposed. If you look at this expression here, you will see that it is the same as this expression here. This expression here and the expression in brackets here are the same. It means that if you define omega as the q dt q qt, if you define it, that means that that tensor that you get is exactly the same thing as the negative of its transpose. If a tensor is negative of its transpose, then that tensor is Q. It's antisymmetric. Go back to week 7. You will see that we defined its Q tensor there as a tensor that is negative of its own transpose. So we have proved that the tensor formed by differentiating Q with respect to T multiplied by its transpose is Q, where Q is the orthogonal tensor. That is the second result. Let me see what people are saying in the chat room. Okay, no nothing. Okay, so we have gotten a second consequence from the fact that identity tensor is a constant tensor. Constancy of the identity, we are going to now define what is an angular velocity. We are going to see what angular velocity is. And this is the most rigorous definition of angular velocity you can get. Consider a rigid body fixed at one end. For example, the spinning top. It is given a rotation RT from rest. Giving it a rotation RT is the same thing as operating the tensor R on its original location, which will vary from point to point. Now, if that is true, we can differentiate that equation. If we differentiate the RDT, remember that R is the original position of the top. So it's a constant. So if you differentiate the small RDT, it's said as the big RDT multiplied by R naught. But R naught itself can be obtained as small r over big R. So you can you can pre-multiply. We cannot divide by tensor. So you can pre-multiply this equation by big R inverse. So that small r naught is big R inverse RT. So big R inverse plus R, this together gives you small r naught. So that's how we got this equation. Therefore, if we define B, where B is the derivative of R, of the position vector R with respect to time, which is this as dr dt multiplied by RTR. Because R being a rotation, you know, a rotation is a proper orthogonal. So the inverse of a rotation is simply its transpose. That's another thing you remember. And which therefore is certain as this omega R. Remember the omega, we defined omega before as simply the tensor obtained by this quantity, dq dt of q. That is the definition of omega. So if that is the case, you now have that V is equal to omega R. But because omega is a skew tensor, and every skew tensor has a vector cross, go back again and remember that if a tensor is a skew tensor, if this is a skew tensor, then there exists an omega cross. So if you replace this big omega with its omega cross, you now find a proof that velocity is simply omega cross R. It's just an effortless thing because we first of all proved that omega must be skew. We knew that omega is skew, and if it is skew, it has an omega cross. We have noticed that every skew tensor has a vector cross. So that's it. So omega defined by this expression, the axial vector of this is the rotation function, and it is called angular velocity. This is where angular velocity is actually defined, and angular velocity is simply omega cross R. So that is the third consequence of the fact that the identity tensor cannot, when you differentiate it, it gives you zero, because it is what makes this quantity skew. It is the constancy of the identity tensor that makes this tensor to be a skew tensor. So now we are getting to our fourth example. When I say it's example 2 here, that is if we take all the examples we have done before as just one example. We saw in the previous chapter that a tensor belongs to its own Euclidean vector space, which is a cube with a scalar product. You know, a tensor has a scalar product. Consequently, there exists a scalar magnitude for all A that is a tensor. The magnitude of A is the square root of the inner product of A with itself, which is the trace of AAT or the trace of ATA. These are things we have defined before. These are things we have defined before. So consider the magnitude of a scalar. Let us say you have, consider the magnitude of a scalar dependent tensor. Sorry, it's a tensor that is dependent on a scalar. Let us say its magnitude. Its magnitude will be a scalar function. So phi squared is equal to the inner product of A with itself, because the magnitude is the square root of A scalar product with A. So we can differentiate this scalar equation. ddt of phi squared, remember, ddt of phi squared is simply 2 phi dt, phi dt. That's a scalar, it's easy to do. And the second one is easy to do also, because we are taking it from the, let us see what number. We are taking it from the 7th. So imagine in this 7th thing, instead of t and s here, but suppose you have t and t. So it will be dtt double t, and then t double dt dt. And because this is commutative, because there is commutative, order is not important here. So that is how we got, that's how we got this one. So we have the a dt scalar product with a, or a scalar product the a dt, which is written as 2 the a dt with a. Therefore, the phi dt itself is d dt of the magnitude of A, and is equal to, how do we get this next quantity here? Is equal to 1 over the magnitude of T, the A, the T, the T. How do you do that? If you are not finding this line easy, note that it's coming from this place, because here, you know, the phi dt is multiplied by phi here. So you will carry this phi to the other side. That's what we can, and we remember that this phi is defined as the magnitude of A. So we are remembering that the phi that is multiplying this quantity here, the phi that is multiplying it is the magnitude of A. So we should have added a step here where we have 1 over phi. That would have made it clearer, because everything else here is basically the same. This quantity here is the same as this. All that has happened here is that instead of writing A ordinarily, we put the functional dependency explicitly there. That's all. So, which means that all we have done is that if you are dividing the product by something, you can divide either of the two sides. We decide to use the division on the second one instead of the first one. It doesn't matter. If you are dividing a product, you can divide either one with the divisor, and it will get the same thing. So that means that the derivative of the magnitude of a tensor is simply the tensor differentiated with respect to T, inner product with itself divided by the magnitude. That is when you differentiate the magnitude of a tensor, you get this relationship. We go to example 3. In example 3, we want to look at the tensor invariance. To obtain the derivative of the trace of a tensor, take the trace of the differentiated tensor. Trace is a linear operator. It follows immediately that the derivative of the trace is equal to the trace of the derivative. To differentiate the trace, we select 3 linearly independent constants, constant vectors A, B, C. And so what we are trying to do here, we are trying to prove that the derivative of a trace is the same thing as the trace of the derivative. That's what this page is proving. The derivative of a trace is the trace of the derivative. We are not taking it for granted. We are proving it. We are showing that both the derivative and the trace operators are linear. So you can swap them. Now, how do you differentiate the first invariant? Remember that what I have in this big bracket is the definition of the trace of the tensor A. What I have in this big bracket. Now, what is below it is a constant. That constant does not take part in whatever we are doing. But what you have on top here is you'll see that even though this is a product of 3 things, only one of them contains the variable A here. So when you want to do the derivative, it is only the ones that have A that you are going to apply the derivative to, because the other 2 are constant. So that's why you have the A dt here, you have the A dt here, you have the A dt here. Every other thing, so that is not there. Even though it's a product of 3 things, 2 of them are constant, so they do not take part. So when you finish, you will see that this is the trace of the A dt. So let us say the A dt is a tensor. This is the trace of that tensor. So it shows that the derivative of a tensor, the derivative of the trace of a tensor is the trace of the derivative. So if you are taking the derivative of the trace, you take the trace first before you take the derivative. You might as well take the derivative first before you take the trace. And the answer you get in both cases will be the same. More on invariance. The second invariant is not a linear function. It's not a linear scalar valued function of a tensor argument. However, we have the expression A cofactor of A is simply A transpose determinant of A for a tensor that has an inverse. So the trace of AC is simply the trace of this quantity here. If you differentiate, you remember that the derivative of the trace is simply the trace of the derivative. So you can now say that the derivative of the trace is the trace of this quantity. not a very useful quantity, but the relationship is a valid relationship. Let us now go to the third invariant. The derivative of the third invariant with respect to a scalar argument is of momentous importance. It is the basis of the theorem and is fundamental to the study of continuum flow in general. So let us take a look at that. So if I want to differentiate the third invariant, this is not, we are not going to have this as is as when we differentiate the first invariant. Who can tell me why this one will not be as easy? Look at this. I want you to compare when we are differentiating this. We are not going to have it as easy as when we differentiated the trace. Why is that so? Let me remind you, let me refresh your mind by, you remember when we are differentiating the trace, see what we are differentiating. We are differentiating three things. But in that bracket, only one of the three products is a variable. But in this bracket here, every term in here is a variable. So who can tell me why this would be harder to differentiate than that previous one? Why would this be harder? Yes, because here we are differentiating with respect to a product of three. So you remember when you are differentiating with respect to a product of three, you have to differentiate with respect to each of the constituents one by one. So you have to. So what we do here is when we want to find the derivative of this, we will first of all reduce this by noting that the denominator here is a scalar. It's a constant scalar. So we can take it out of the expression by multiplying it on this side. So we are looking at A, B, C, dt of determinant of A, and what we have on the other side is just differentiation of this triple product. So that is, and the differentiation of the triple product is easy because you differentiate only one and have the other two, differentiate the second and have the other two, and differentiate the third and have the other two. That is how you get it. So if you do that, you come and do, there is an artifice here. You know that A inverse A. What is A inverse A, class? What is A inverse A? What is A inverse A? What is A inverse A? Is the identity. So because it is the identity, there is nothing wrong with our inserting it here, because we can insert the identity here without changing the value. So we have inserted the identity in all of this. So that means that if you bracket out this quantity here, dA dt A inverse, dA dt A inverse, dA dt A inverse, what you have left is AA AB AC. What you have here is AA AB AC. What you have here is AA AB AC. If you look at that, you just see that it is simply the trace of the ADT times AA AB AC, which are three linearly independent vectors, because when A operates on small a and A operates on small b and A operates on small c, if A, B, and C originally are linearly independent, AA, AB, and AC are also linearly independent. And if you now take the ABC that is on the other side and use it to divide this, you have, in addition to this one, what we define as the determinant of A. So the derivative of the determinant of the tensor with respect to T is simply the trace of the ADT A inverse, all multiplied by the determinant of A. And this is a momentous theorem called Liouville's theorem, and we continue constantly referring to it in continuum mechanics. That is the most important of the consequences that we have seen so far. So just credit that and have that to your right hand. Okay, so we have, in the first 18 pages, we have dealt with the simple cases where you have tensors, but you are differentiating them with respect to scalar argument. Despite the fact that those are easy things, and we still have some interesting and important results. Now, we are going to the difficult area where you are now having that what you are differentiating with respect to is itself either a vector or a tensor. This is where the work really starts. We have just been playing so far. You see, when the domain of definition itself is made up of large objects, the task of differentiation becomes more demanding, and such problems are standard in continuum mechanics. And these are examples. For instance, the strain energy function is a scalar quantity, yet we can differentiate it and obtain strains, which is a tensor. The stress function is a scalar quantity. You can differentiate it and obtain stresses. So we are dealing here with differentiation of scalar functions of tensors, which is stress. The velocity gradient, which is you are differentiating velocity with respect to a vector, and it's going to give you a tensor. Why? We will see why. Here we are differentiating a vector field defined on a Euclidean point space with respect to a position vector on the points of E. In this and several other derivatives of interest, the domains are no longer in the real scalar space. You are now moving away from your elementary math that you used to think was advanced math when you are doing it. But by comparison with what we are going to do next, you will see that those are elementary things. So I'm not going to get to the end, but I will just give you, I whet your appetite, expect you to go and read this chapter to the end so that we can continue next week, because you are very dull earlier in the day and I want to let you rest. When we are in a vector domain, I'm just trying to show you what the problem is. When we're in the vector domain, X and H are vectors. So if you want to now differentiate a function of the vector X with respect to X, if you try to apply the scalar rules you had, you can say, okay, it is the limit at H tends to the 0 vector of function of X plus H minus function of X. You are still okay so far, but now divided by H. You cannot divide by a vector. It is not possible. You can't divide by a vector. So the elementary differentiation formula that you have been carrying all along breaks down completely here. It creates several problems. For example, division by vector is not defined. Division by tensor is not defined. That's one problem. Problem number 2. Whereas when you say H tends to 0, when H is a scalar, there is only way H can tend to 0. If its absolute value is getting smaller and smaller, it's tending to 0. But a vector can approach 0 in several ways. Similar arguments arise when the argument is a tensor. It's even worse. So it is an error. This expression here is a complete error, and it is coming because you are differentiating. You are dividing by a vector, and vector division is not possible. The approach to solve this problem is twofold. Recognize that vectors and tensors live in their respective Euclidean vector spaces, and where the concept of length is already defined. In any Euclidean vector space, the concept of length is defined. Use the above to extend the concept of directional derivative, which you did last time, to include the derivative of any object from a given Euclidean space with respect to the objects from another. Such a generalization is called the Gateau differential. And we are going to continue to the end of this chapter by explaining what the Gateau differential is, and we use it to solve all the problems that we have. But I'm not going to do that today. I'm going to let you go rest. And when you go to rest, this is what you are going to do. You are going to go back to your last session's note, or is it last time? Well, it's difficult to know now because some people went on strike for 8 months, and I don't even know which section we are in now. Whether it's the session before they went on strike or after the strike, I don't know. But you remember that we did directional derivative. Go and read that again. Go and read all we did in that again. Go find your notes on that. And then secondly, read this chapter. This chapter has another 8 pages left. Read it 8 pages to the end. So that when you come next week, you are not going to come and be sleeping in class, and I will be asking questions and you will not be answering. So class, we are going to end it there today. I'll meet you again next week. So please be more prepared next week to meet me, and so that the class will be more lively than it is today. Thanks very much. Bye-bye.